இப்போ
சார் நீங்க சார் 10:30க்கு கொடுங்க சார் ரெக்கார்டிங்.
ஓகே.
நேத்து அனுப்பிச்ச வீடியோ வந்து 2 hours போகுது. 2 hours வீடியோ.
ஓகே ஓகே. நான் 10:20க்கு இது 10:20 கொடுத்துறேன்.
எக்ஸ்ட்ரா வருதா கொஞ்சம்
10 minutes தானே முன்னாடி கொடுத்துறேன்.
சார் எஸ் சார்
10:20 should be nice. Okay. Sandy sir சரி தானே?
Sure sir, no problem.
Yeah, done. So 4 பேர் அங்க போயிருக்காங்க. ஓகே.
ஆமா சார், அங்க உள்ளது இங்க டிஸ்கஸ் பண்ண வேண்டாம்னு HOD சொன்னாரு.
That's good.
What to discuss now, you discuss over phone, not through Google Meet னாரு.
Exactly.
So Vijay Kumar sir has come.
ஆமா.
பாஸ்கர் சார், நீங்க லிங்க் செக் பண்ணி பாக்குறீங்களா? எனக்கு பக்காவா வருது. உங்க
நான் இப்ப பாக்குறேன். I can check in my mobile, sir, mobile.
ஆமா.
Yeah, I'll check. வருது சார். நீட்டா இருக்கு சார். பர்ஃபெக்ட் சார். பர்ஃபெக்ட். வருது சார். கரெக்டா இருக்கு சார். HOD sir, welcome. Good morning.
Sir, welcome, sir.
Good morning, sir.
Good morning, sir.
Good
Please.
morning. Good morning, sir.
Good morning, sir. Welcome. Dr. Stanley, sir.
Yes, sir.
HOD இருக்காருங்களா? HOD want to
He is there, sir. HOD is there.
talk to? Yeah. If you want, you can just tell him that the speaker has joined. You can welcome him.
Okay, sir.
நீங்களும் welcome பண்ணுங்க. You can also welcome him.
Right, sir. He's
Greetings, sir.
okay, sir.
Greetings, sir.
Good morning.
Good morning. Good morning, Dr. Venkatesh Rao, sir. We are happy to welcome you.
Very good morning. Thank you very much, sir.
Thank you, sir. HOD, sir. சார் நம்ம இன்னும் 5 minutes இருக்கு இல்லையா? நம்ம ஆமாம் 21 ஆச்சு. நம்ம கரெக்டாக இன்னும் ஒரு 3-4 மினிட்ஸில் நான் ஒரு 2 வார்த்தை சொல்லிவிட்டு நான் இது மாதிரி என்ன நீங்கள் தானே இன்ட்ரடியூஸ் பண்ண போகிறீங்க? பிரீதா மேடமா? ஓகே சார். நீங்கள் கொஸ்டின் செஷன் பார்த்துக்கிறீங்க. ரைட் 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 சொல்லிவிட்டு சரி ரைட். அவர் வந்து பார்த்துட்டு போனார் சார். அவரோட ஸ்லைடு காமிச்சார், ஃப்ளாக் போட்டது காமிச்சார். நல்லா நோ ப்ராப்ளம். ரைட். ஆமாம் சரி 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 சார். ரைட். ஓகே சார். ஓகே சொல்லிடுறேன் ஒரு வார்த்தை. ஓகே. Good morning to you. Hello, sir. HOD, sir. Shall we start that day?
So shall we wait for 2 or 3 minutes? You can wait, sir.
Sorry, sir.
You can wait 2 more minutes, sir.
Okay.
Just 2-3 minutes.
Stanley sir,
Yeah.
shall we proceed sir? Time 10:30.
They are asking me to wait for 3 minutes, so
Okay.
சார் நீங்க ரெடியா இருக்கீங்களா? வெல்கம் பண்ண. பிரீத்தாவா? ஓகே. ஸோ அப்போ நான் பிரீத்தா பேரை சொல்றேன், நீங்க கொஸ்டினை நீங்க பாத்துக்கிறீங்க. ஆரம்பிச்சிடலாம்னு நினைக்கிறேன் சார். டைம் ஆயிட்டு இருக்கு. ரைட் சார். Right, sir? Sir, shall I start?
Yes, sir.
Right, sir. So, good morning to one and all present here. Let us start this day's proceeding with the blessings of our Lord Almighty. And I am very happy to have all the participants as well as today's expert speaker, Dr. Venkateswara Rao, Professor of Nanotechnology, Head Center of Nanoscience. We are happy to have you among our midst. Now, may I request Dr. Preeta to introduce the expert speaker to the gathering.
A very good morning to one and all. It's my great honor to introduce our speaker, Dr. Venkateswara Rao. He is an eminent resource person in the field of nanotechnology. He has wide range of teaching experience in quantum mechanics, nanomaterials, and sensors, etc. He completed his doctorate in University of Hyderabad and postdoctorate in Johns Hopkins Medicine, USA. He started his career as a lecturer in physics in 1997, and now he is the head of the departments of Center for Nanoscience and Technology, Institute of Science and Technology, Jawaharlal Nehru Technological University, Hyderabad. His areas of specializations are nanomaterial synthesis and characterization, gas, glucose and humidity sensors, solar cells and batteries, cancer imaging. He has 3 patents, 330 international publications, and published 15 books. He has completed 2 UGC, 1 DST, and 1 nano mission projects. He is also doing collaborative work with in India and Japan. He has guided 14 PhD scholars and many students in postgraduate level. He is a gold medalist in MSc, and also he is holding the Raman Postdoctoral Fellow. He has also received the Best Teacher Award from the Government of Telangana and ITAP Award. With a short note, now I would like to hand over the session to our speaker. Sir, please, sir.
Good morning to one and all. Thank you very much for the introduction. Are you able to see my screen?
No, sir. We are not able to see your screen.
No, sir.
Okay, I'm just 1 minute. Now it's okay, am I right? Hello?
Yes, sir.
Fine, sir.
Yes, sir. Fine, sir.
Yeah.
Fine, sir.
Thank you very much for introducing me and giving a chance to talk with you all. Today, I'll be talking about nanostructures, sensors. Basically, I'll be talking about sensors. In that sensors, I will be talking about gas sensors and glucose sensors. So before I am going to talk, what are the takeaways after my talk? That is a very important thing you should concentrate. The first point I will be talking about what is nano, why nano, is it nano new or old? If old, why we did not study it till today? These are the basic things I will be talking before my gas sensing. Under the gas sensing, once again, I will be talking some of the basics of gas sensing and some of the work case studies of my research. And similarly, in case of glucose also, I'll be talking some of the fundamentals of biosensors and then glucose sensing. These are the takeaways of my presentation, my talk. However, I'll be giving you the slides in the PDF format. So if you see here, if you see this, the nanoparticles have got n number of applications, starting with textile, biomedical, healthcare, food and agriculture, electronics, environment, renewable energy. So you may be thinking what nano kind of things. Textile means there are once again a variety of applications, cloths which need not wash, antibacterial cloths, antibacterial undergarments, some surgical doctors related materials where antiviral coatings could be done. These are all some of the interesting applications of the nanotechnology, nanoparticles towards the textile applications. Coming to the biomedical, once again, it's a vast area, starting with imaging and imaging of cells and drug delivery, cancer therapy, biomarkers, molecular tapping, bone growth, biocomposites, drug controlled release. There are once again a group of interesting applications, even MRI agents, imaging, antibacterial, the n number of applications are available with the help of nanotechnology. So, however, we will be talking gas sensors and chemical sensors. Basically, how these gas sensors are very important in this case of nanoparticles and nanotechnology kind of things we'll be understanding here. You may be wondering what quantum computing. Quantum computing is the one area where people are trying to develop rather than a normal classical computer. Whatever the computers we are using are classical computers where binary 0-1-1-0 combinations will be available. If quantum computer comes into reality, then there are 0-1 combination of 0-1 spin, that is the spin, electron spin, as electron spin up down, a combination of up and down is possible. So there will be a lot of, once again, there will be a lot of applications related to quantum computing. So these are all broadly, I can say, nanoparticles have got n number of applications. Why nano? Why not other things? That is the first point you need to understand. If you see the smallness, the advantage of smallness, if I broadly just a normal people who did not study anything also, if I ask sugar powder and sugar cubes, which one will mix very fast, then everyone can answer immediately that sugar powder. Why? Because smallness will be more chemically active. Chemical reactiveness increases more. But what all the properties that will change or that will come newly, something different? Color may change when you reduce the size of the particles. Like if you see here, gold normal color, but if you reduce the size of the gold, it will become brick red and then blue and then color will change due to the plasmon resonance and other concepts. Actually, I will not be going in detail about that. So color, melting point, strength of the material, conductivity of the material. Conductivity means resistivity, even reactivity. And these are all some of the interesting properties where you can tap that particular property. Based on that property, you can engineer your applications. Let us take gold nanoparticles. As on today, these gold nanoparticles people are using in different imaging applications, and because of its size peculiarity. That means when you reduce the size of the particle, the color will be changing from different colors. So what I mean to say here, whatever the fundamentals, whatever the size matters, whatever the fundamentals like color, fundamental properties of that particular materials will be modified when you reduce the size of the particles. Then you may have to ask me a question. Why not in the case of milli and micro? Why only in the case of nano? That is the another thing you need to understand before you are going to our next slides. That means the first takeaway here is why only nano, why not milli and micro? What are the differences between milli materials, micro materials and bulk materials when compared to the nanomaterial? Why so special about the nanomaterials? This point is a very important point you need to understand before we are going to our particular research topic. Let us take a simple example of a sphere. Take a sphere whose basic formula for sphere is 4/3. Volume of a sphere is 4/3 pi r cube, and surface area of a sphere is 4 pi r square. These are the fundamental formulae we know. Now I will ask you people, take 100 nanometer diameter sphere and take 10 centimeter sphere. So I'm asking you to find out volume of a sphere whose diameter is 100 nanometers, whose diameter is 10 centimeters, otherwise 100 meters, let us say 100 meters. So here, then, so if diameter is 100, then I can say 4/3 pi r cube, then I convert into radius into diameter 4/4 pi d cube by 6, then I substitute 100 nanometers there, then I will be getting the volume is approximately 5.24 into 10 to the power of minus 22, and the surface area will be 3.141 into 10 to the power of minus 14. Here something interesting phenomena will happen. In case of 100, here high number will be there, but here this much low number will not be there. You need to understand the difference between in the nano size and when compared to meters and centimeters. I think you are understanding. Now I will be taking surface to volume ratio. Surface to volume ratio. If I take surface to volume ratio and if I calculate, then what happens? The surface to volume ratio is going to be predominantly increasing, approximately greater than 10 to the power of 7. Which is significantly larger than a micro-sized particle. Even micro-sized, or if you take a centimeter level, if you take a 100-meter level, if you take a millimeter, all these things will not be having this much difference here. You need to understand the surface area, because here 10 to the power of minus 14 is one interesting phenomena. So what happens here? This gives an approximate surface area to volume ratio, which is more than 10 to the power of 7. As the surface area to volume ratio increases, so does the percentage of atoms at the surface, force becomes more dominant. This is the point we need to understand when we are talking about nano. Whereas same problem, if you solve it for 10 centimeters or 100 meters, it will be entirely different. It will not be like this 10 to the power of 7. That much predominant value will not happen. So here surface to volume ratio is the one phenomena which we need to understand in case of nano when compared to the milli and micro. That is the first point we need to understand. Generally, accepted material properties are divided from bulk, where the percentage of atoms at the surface is many. These properties change at the nanoscale level. That is the difference you need to understand. The first takeaway of my talk is surface to volume ratio increases predominantly, abnormally. This point is the first takeaway of my talk. Let us take another simple example. First, we took it a surface sphere, and then I will take a cube whose the surface area formula 6 into length into breadth, and volume formula L cube. So if you substitute and if you go on cutting into P, you can understand the difference between here also, the surface to volume ratio. So smaller means more surface area. And for example, sugar and salt in water, more reactivity. This is how very simple point, very simple thing is nothing great. What I want to tell you is smaller. The smaller means more reactivity. More reactivity is nothing but more surface area. So when you are coming, especially in the case of nano, there is a predominant surface area increase is happening. That we need to understand. This is the first takeaway of my present talk. Then, if you take a simple example, same cube, go on cut into pieces to nano level, then you can cover almost a big football ground. That is the surface area. That much of surface area is going to be increases. High ratio of surface area to volume. This is the point I am concentrating. This is the point you need to understand very clearly. This is the point, first point. The takeaway of this is, the takeaway of the talk of the first point is surface to volume ratio increases abnormally. This is the first point I want to tell you all. Coming to, let me leave. So this is for the same thing. I want to also prove that. Let us take the size of the particle on x-axis and surface to volume ratio on y-axis. So see here, this is millimeter. It is nanometer. Okay, got it. So it is in millimeter. It is in micrometer. But see here, what is happening at 100 nanometers? 100 nanometers, something different is happening. What is that? There is a increase in the surface to volume ratio. This is the reason why we are very much interested in between 1 to 100 nanometers. For that reason, everyone is talking about nanoparticles, nanotechnology. So the definition of nano is, if a material is in the range of 1 to 100 nanometers in any dimensions, like not 3 dimensions, any dimension, any one dimension, then we can say they are the nanomaterials. This point, if you understood, then the other things will be very, very simple. So till now, what I was trying to tell you is, when compared to bulk, micro, and milli, nano is something different. Why it is different is for this reason. What is the reason? There is a increase in the surface to volume ratio. This point you need to understood. For that reason, we took an example of a sphere, and we also took an example of a simple cube, and we calculated it and we understood. this is the first takeaway you need to understand. Coming to the next, I just don't want to talk about quantum mechanics and other things here. So another important, the next point what I'm targeting is it new? Nano is new? Is it old? Then my answer will be, it is there from years together. Even our grandmothers know how to prepare carbon nanotubes. With the help of combustion reaction, they prepare causal, which we keep for eyes to blacken, or to some traditionally people will keep for eyes. That is also, if you use them in a scanning electron microscopy or a transmission electron microscopy, you could see micro carbon tubes or nano carbon tubes. So they may not be very precisely formed, but they are there actually. And even we know our very rich people in villages, they eat in silver plates which were made up of gold flowers in the middle. When they put hot rice on it, small amount of nanoparticles will go inside, and that will be good for health concepts. Even we know very simple things like babies, when they're born, after first feeding we do with silver cups. Why? Because silver is an antibacterial. When they are on the surface, so when you are giving food, some nanoparticles will go, and that will be good for health. Kind of simple concepts. So what I mean to say here is, nano is there, but why very predominantly people are talking recent days? Because people were invented different types of microscopies. Earlier we used to have optical microscopies, which we could see only micrometer range. When the electron optics came into reality, and hence people started developing different types of electron microscopies like SEM, TEM, atomic force microscopy, STM. These are all things made to visualize things in a better way, and hence the property of the morphology, the property of the surface also is explaining to understand more effectively. That is what the basic point we need to understand here. Let us take a simple example. Peacock feather. If you see the basic thing is you need to understand the nature to do whatever research, to do whatever transformation. Only one boy came and told that apple is falling due to gravity. Apple is falling before also, apple is falling now also. Only one person could see the gravity concept, and he could derive the formula, capital G, small g, all these concepts. So nature need to be understood. Being a science student, being a technological student, being a researcher, we need to see the nature in a different, with a scientific eye. That is what is required as on today. So if you take a simple example, peacock feather, they look very bright in color, and they are self-cleaning. When sun falls on it, we see different colors. What is happening then? What is happening? So if I zoom it, they look like this. If I more zoom it, they are like this. And if I am going zooming, I could see that the morphology is something very interesting. They are all like holes which are in a particular manner. Nano size holes repeated as a pattern on the nanoscale range. So my interesting phenomena here is, you know, the physics and chemistry fundamentals, why these colors are coming. You can explain with whatever the surface tension formula, hydrophobic nature, and luminescence concepts, whatever it might be. But if you see this image, then you can also explain in a more effective manner. What simply I want to say that if I can mimic in the nanoscale range this kind of structure, then that material will have this particular property. You understood? So mimicking, biomimicking of the nature, you need to understand the nature, from there everything. So if you want to develop something like these colors, different bright colors which are self-cleaning and no one is cleaning them, in spite they look very interesting, very bright colors, peacock feathers. So what I mean to say is, so these are the pictures based on imaging. It may be scanning electron microscopy, tunneling electron microscopy. So you could explain more effectively the science and technology. Similarly, you see the butterfly feathers in different colors, in a different interesting patterns. How this pattern is coming? What are the colors? So if once again, if I zoom some of the butterfly feathers, some of them are like a jib kind of rib kind of structures. You could see very clearly here. And you see here, very interesting phenomena, very interesting surface phenomena. So what I want to say here is, whatever the science you know, whatever the text, the basic fundamentals you know, you could explain in a better manner with the help of this kind of imaging, this kind of special kind of imaging. So that if you can design, if you can prepare, synthesize a material, this kind of patterns, then there is a possibility of mimicking of this kind of structures. Another simple thing is lotus leaf. We see lotus effect, we know very well, surface tension and hydrophobic nature of that particular leaf. There will be small rods. If I zoom it, they are like this. If I zoom it, so whatever I could explain, I could design, I could develop more concepts with the help of this kind of microscopies. That is what I want to tell you. So here, simple, just see nature. By see here, if I quote some of the nanomaterials here, the fogging, anti-fogging nature in rainy season car travel, otherwise in restrooms, hot water, after hot water bath, fog will be there. And this kind of things could be understood in a more effective manner. See, even like the Superman, Spider-Man, all these things. So if I go on, zoom it, I could say a pattern, a clear patterned systems, a clear pattern, a clear kind of cubes, a clear kind of structures we could see very clearly. So the basic things could be explained in a more effective way. Nature could be understood with the science and technology, and from there you can mimic. So all these concepts, interesting concepts, whatever we say is some of these concepts, like this kind of. So here, from these slides, what I want to tell you are 2 points. Number one is nano is not old. Nano is not new kind of thing. It's old. But due to the microscopies available, we could understand more effectively. Then you may also ask one more question: why nano related? You are telling so much about nano. Why products are not available as on today in the market? Why products are not available? Then I'll say like this. So I can prepare 1 gram of nano material, very like this particular structure. I can prepare 2 grams. But if you ask me to prepare 1 kg, then reproduction is a very, very tough task. That means process engineering is a tough task. You need to understand the process engineering. That is where the nanotech technology is stuck as on today. That some of them could do process engineering, but the chemical engineering, the process engineering to prepare different types of materials in higher levels, this is a tough task as on today. That is the reason people are unable to do. So this is the second takeaway of my talk. The first takeaway is why nano? Nano surface to volume ratio predominantly increasing. That is my first point I was trying to tell you. The second one is nature inspires the science, and nature should inspire the scientists and technologists. From there, things will be more better. So these are the 2 takeaways I gave till now. Coming to my next topic, introduction to sensors. The term sensor is similar to sensing organs which are there in our body. As on today, rapidly sensors were used in everywhere, anywhere. If you see taste, hearing, sight, smell, touch, all these are some of the sensors. The problem here is, if I say hearing, I can say that it is loud or it is low. I can't say how many decibels of sound is coming exactly. So sensors will do that point. That means how much, if I have a sound sensor, I can see that how many decibels are coming. Let us say sight. In this case also, I go on zoom it, I go on increase it, I telescope or microscope. Smell also, I need to say bad or good, but I cannot quantify it, exact number I cannot say. That is where the sensors plays a very important role. So we want to say a particular number based on particular phenomena, whatever it might be. The phenomena is different, like Seebeck effect, Thomson effect, Peltier effect, otherwise photoelectric effect. Based on some physical phenomena, we want to measure some of them, and based on that, we want to understand. So a simple chemical sensors in earlier olden days, people used to take the samples and they analyze it and they take some time and they see and they study and they will come with some explanation. But as on today, our police people have got alcohol breath analyzers. Immediately they can say how much of alcohol the person is consumed. How they will say when they based on their smell which is coming to this mission particularly, it will give us some particular number. So the level of alcohol consumption. What is the basic phenomena? There will be some chip, some material will be there. When alcohol gases are going there, they may oxidize or they may reduce. Oxidization may happen or reduction may happen depending on the type of the gas and depending on the type of the material. So there will be we can measure voltage or current or resistance because of this oxidization and this reduction. You know very well what is oxidization and reduction. Absorption of electron or giving electrons. These are the two phenomena will be there generally. So when this is happening, based on that, so that the mission may measure voltage, the mission may measure current, the mission may measure resistance. Based on that, we can say normalized value. From there, you can say whether the particular person has consumed the alcohol or not. So as on today, most people are using different types of sensors, starting with environmental sensors, medical diagnosis, healthcare, automotive is the n number of sensors. Depending on the cost of the car, you will be getting different types of advantages like auto lock, otherwise n number of things like sensors, different types of sensors, defense, machinery, manufacturing, space, security. Most everywhere this type of sensors were there in all the fields. As an example, let me one minute, I'm just able to. Oh, sorry. Are you able to see my screen?
Yes, sir.
Yes, okay. So this is a simple example, manless car, self-driving cars.
In Sweden, with real customers in the driver's seat. The unique Drive Me project is a part of Volvo Cars' journey towards a crash-free future. Volvo has now designed a complete system solution. Multiple radars, cameras, a laser, and ultrasonic sensors monitor the complete 360 view of the surroundings. A network of computers processes the information, high-performance GPS, and a cloud-based 3D digital map, continuously updated with real-time changes in the traffic environment. If anything fails, there is a backup solution, just like in an aeroplane. This includes vital components such as computers, sensors, steering, and brakes. On the road, the car is able to handle even the most complicated scenarios. The technology is so reliable that the driver can focus on something else without having to pay attention to the traffic. Just like good drivers, potentially critical situations are approached with sensible caution. And in an emergency, the car reacts faster than most humans. When autonomous driving is no longer available due to exceptional weather situations, technical malfunction, or reaching the end of the route, the driver is prompted to take over again. If the driver doesn't take over in time, the car will bring itself to a safe stop. With the Drive Me project, Volvo and...
So these are some of the interesting situations, interesting applications for the mankind to become more effective and safer and better life. Luxury driverless cars with embedded sensors. Future transportation may have this kind of interesting phenomena. We may not even realize it, but sensors are found commonly at the household. They are in electrical services, switches, refrigerators, climate control, toasters, everywhere, almost all the fields. There are different, or even we know that normal thermometer, the temperature thermometer, basic concept is increase in the volume is normalized with respect to particular temperatures. That was seen as a normal thermometer. So, coming to the basic definition of a sensor is, a sensor is a converter that measures physical quantity and converts into a signal. The signal may be current, the signal may be voltage, the signal may be resistance, the signal may be pressure, the signal may be force, the signal may be velocity, the signal may be time, whatever it might be. But a sensor is a converter that measures a physical quantity and converts it into a signal which can be read by an observer or by an instrument. A simple way of understanding a sensor is the one where you can use, I told you, physical phenomena. What are the physical phenomena? Maybe mechanical energy, maybe an electrical energy, maybe a chemical energy too. There are the other chance of chemical energy also. And then you may be actuator may be a velocity, acceleration, force, pressure, temperature. Otherwise, current, voltage, capacitance, and inductance. This is how you need to understand. Basically, a sensor acquires physical parameter and converts it into an optical or electrical or mechanical signals which are suitable processing. So I will say optical sensors, basing on different like see, when a person moves, lights switch on. When a person not moving, lights will switch off. A kind of simple optical sensors, and electrical sensors and mechanical sensors, force sensors. There are n number of sensors depending on the physical phenomena. So I will bring, because will be, let us say, a simple gas sensor setup, a simple kind of a sensor. See, it will be like this. See, a normal gas is coming here, analyte, and then a physico-chemical interaction will happen here, and then material will be there here, a transducer or a material, and this will go to an interface circuit, and from there you can see measure is simple. This is how we can broadly say a sensor looks like this. A sensor is a technological device that detects and sends a signal, physical condition and chemical compounds based on the performance, based on the phenomena, physical phenomena, whatever we are using. As on today, there are n number of sensors are available in the market. However, there is always a chance to improve the properties, maybe the cost, maybe the temperature controller, maybe the sensitivity, maybe the selectivity, and number of things, the size, anything. There is always a chance of incremental development of science and technologies based on whatever as on today. So you can think of interesting phenomena. If you see in the olden days, in the mines, first people used to send birds inside. If bird is coming after some time, people think that, so there is an oxygen inside that, and so they can go and they can work. Otherwise, people used to take lamps, the kind of lamps where lamp will switch off after some time if oxygen is not there. So similar concepts people used to use in the olden days. But as on today, people are developing a number of things. So till now, what I was trying to tell you is sensors. And after that sensors, I brought you slowly to gas sensors. And from the gas sensors, what I am trying to tell you, mechanism of gas sensors. So there are n number of sensors. Once again, I was trying to tell you electrical, mechanical kind of sensors. So now we are going to talk specially about the gas sensors. Means when gas is coming, there will be a sensing phenomena like alcohol breath analyzer, LPG gas sensor, NO2 gas sensor, carbon monoxide gas sensors. There are n number of gas sensors are available in or around us. So we need to understand what is the gas sensor coming to. So first I gave you the concept of sensors, and then I came to gas sensors. And then this is the next 3 slides, 1, 2, 3, 4, 5. These 5 slides are the takeaways, the fundamentals of mechanism of gas sensing. Try to concentrate on this. These are the next 5 slides are going to play a very important way of understanding. See, the basic problem is if you understand the basic concepts, then you can think incrementally and you can think your own way and you can add innovation to your thinking and you can design something new. That is what is required. People don't understand the fundamental thing and start research means it's a tough task. Like without a proper pillar, if you do something, then there will be a problem. So the next few slides are very important. The core concepts of sensing, gas sensing phenomena. So in this phenomena, what I am trying to tell you is when you have a type of material, a simple, like let me go to here. Yeah, it's a simple figure. Say a probe sensing material. So what I am trying to tell you, here I am keeping nanomaterial. And I am sending gas. And what happens here? I am also giving a little bit of voltage. I will tell you to complete the circuit. And I am measuring resistivity. So what I am trying to tell you here, I told you, you can measure voltage, you can measure current, you can measure resistance. If you measure current, then it will be amperometric gas sensing. If you measure voltage, it will be potentiometric gas sensing. If you measure resistance, it will be chemoresistive gas sensing. See, I have my own setup because the type of gases I am doing my research and the type of materials I am working are suitable for chemoresistive sensing setup. So that is the reason I am going to concentrate now on chemoresistive gas sensing setup. That means what is the fundamental phenomena which is happening when a material is there and on that nanomaterial when gas is going and hitting this material, and what is happening for the resistance. I am going to measure a resistance. What is the resistance measurement? You can use a simple multimeter to measure keep in the resistance mode. But the sensitivity matters. How sensitive, how much resistance variation is happening when gas is entering onto the material is the fundamental phenomena we need to understand. So what we started sensors and we came to gas sensor, and from there we came to chemoresistive gas sensors. That means I am going to measure resistance when gas is going to the material. When gas is going to the material, what is going to happen? There may be a phenomena of oxidization. There may be a phenomena of reducing. The gas may oxidize or the gas may reduce. These are the two phenomena will be there. Once again, the type of the material. Is it an N-type material or is it a P-type material? Some gases are reducing, some gases are oxidizing, depending on O2, O3, NOx, Cl2 are oxidizing materials, and these are the reducing. So N-type, some of the examples of N-type materials, TiO2, ZNO, SNO2, and some type of P-type materials. So what happens when gas is going onto the material? There will be a oxidization or reduction will happen. When oxidization, if it is an oxidizing gas and if it is a P-type material, then it will be the resistance, whatever we are measuring, will increase. If it is and that means conductivity increases. You can say in another way, conductivity increases. In the same way, if it is N-type and reducing gas, resistance decreases. In a P-type, if oxidizing gas, then resistance decreases. In this case, resistance increases. These are the four possibilities we have totally if you are talking about chemoresistive gas mechanism. It's a simple phenomenon. So what are the factors? What are the important factors of the materials? Let us say parameters of gas sensing materials. Let us say I am telling you I am using some material here, N-type or P-type material. So what are the parameters? The crystal chemical composition, crystallographic structure, catalytic activity, surface structure, and morphology. These are all going to play a very important role on the parameters of the sensing mechanism. What I mean to say is, if I have rods, if I have a circular thing, if I have a flower kind of structures, then the sensing property is going to vary. What I mean to the same material, but if I prepare the same material like a rod, if I prepare the same material like a different structure, then the property of the gas sensing properties are going to be varied. That means morphology plays an important role. Surface structure. Let us say the same material I can prepare in hexagonal, the same material I can prepare in a cubic structure, then the sensing parameters are going to be varied. This point you need to understand. Means the same material with different parameters are going to vary the sensing properties. What are the sensing elements? Like thermal stability, at what temperature the sensing is happening, selectivity of gases, gas response. Let us take, I took cool drink and someone took alcohol. So the breath analyzer is also sensing cool drink, is also sensing alcohol. Then the response is selectivity of the gas is not good. And sensitivity is also very, very important. How much quantity the person took the alcohol, and then operating temperature plays a very, very important role. That means you need to supply always energy. Let us say this gas sensor works only at 90 degrees centigrade. Then I need to always give energy to them. I need to give separate energy and rate of response. What is the rate of response? Let us say I am sending a gas. When I am sending, see, this is the time and this is the resistance I am measuring. Why I am measuring resistance? We came to chemoresistive gas sensors. I told you, sensors, gas sensors, chemoresistive gas sensor. There are amperometric gas sensors will be there, potentiometric gas sensors will be there. Potentiometric means voltage you will be measuring, amperometric means current you will be measuring. In our case, we are studying resistance. So when you are measuring resistance, when you are sending gas, what happens? Its resistance may decrease, may increase also. Let us say an example if it is decreasing. And then after particular point of time, saturation will happen. And if you stop, it will go to a particular point. So this is the response time. That means, let us say I kept alcohol breath analyzer in one person's mouth. If it is taking few seconds to give reading, that will be well and good. Let us say it took half an hour. Then he can't always keep half an hour in his mouth and the response time is very heavy. So it should be less and recovery time. That means second person is there. If I want to keep the same alcohol breath analyzer for the second person, if I need to wait 30 minutes, then it is not worthful. I can't make them to wait. So the recovery time should also be very, very less. And ideally, response time and recovery time should be very, very less. These are the very important parameters of a sensor, and these are the properties of the materials. The same curve, whatever I was trying to tell, it is like this is the response time, this is the recovery time, and the sensitivity simple formula I can say S is equal to RA, resistance before gas, RG, resistance when gas is there, divided by RA, the selective percentage you can measure. Response time, recovery time, and stability also plays a very important role. Sensing material and interaction between the sensing material need to be understood. This is the very important concept you need to understand. Once again, I am here putting in the form of a circuit, which I was trying to tell you. And here, see here, this is the material and this is the gas coming out. When this is happening, there are the four possibilities: N-type and P-type, increasing, decreasing, decreasing, and increasing. If I put it in a form of a graphical figure, four possibilities are there: N-type and P-type, reducing gas. Conductivity increases, that means resistivity decreases. Oxidizing gas, N-type, P-type, conductivity decreases, that means resistivity increases. N-type, P-type, reducing gas, once again, these are all some of the possible phenomena which will happen in case of gas sensing. Here, you need to reflect yourselves that the takeaway is simple, very simple. Reduction, oxidization will happen depending on the type of the gas and depending on the type of the material what you are using. And we will be measuring the resistivity in the circuit. This is what the gas sensing phenomena in the case of chemoresistive gas sensing. So, challenges, what are the challenges are accuracy, response rapidly, specific, sensitivity, operating temperature, size of the sensor, maintenance cost, repeatability, durability, eco-friendly. These are all some of the required challenges if you design a sensor. Okay, so that is the fundamentals of a gas sensors. Now I'll go a little bit faster. I took 3 case studies. Why I took 3 case studies are, this is an MTech student who published a lot of papers on SM2O3 gas LPG sensing. This is also an MTech student, and this is a PhD student, however, but this is a different story. I will tell you. So here, 3 case studies are there. I will be going in a very fast here because I want to concentrate once again on biosensors also. So we worked on different type of sensors like electrodes. We used IED, gold IEDs, and aluminum IEDs. Even we worked on flexible sensors also like this. So basically, this is the design. I got in a project in SVRB where we developed this type of gas sensing setup, which is like flow meters, different, this is the analyte gas and this is zero gas. Whatever gas we want to sense, we have this. And these are like a Cathali 6 digit, that means micro ohm change also could be measured. This is a chamber where I'll keep material here. There will be a heater will be there. I can heat, and sensing material will be there. And then this connectivity will happen here. And based on that, I can sense the material. So a simple thing is like we prepared a graphene SMO2 material and on graphene based, so that oxygen molecules will be there. LPG, when we send it, CO2, H2O molecule, they interact with these materials and oxidization may happen, a reduction will happen. Based on that, you will be seeing different types of curves. So this is a biotemplate hydrothermal synthesis. We took eggshell, egg core shell, egg. We took egg, and from that egg shell we took it, and that shell we took it as a membrane. to prepare hydrothermal synthesis of nanomaterials. Hydrothermal is nothing but we vary different types of, it will be like a pressure cooker concept. At low temperatures, high pressures will be produced, and different timings and different pH concentrations will be taken, and based on that, we will be preparing different types of nanomaterials. And this is X-ray diffraction to study the crystal, optical, FTIR, UV, and other things, and scanning. See here, the same material we prepared, but based on the like rice kind of structures, we got it, and like rods. You could see rods and different hierarchical structures based on temp. See here, and this because of oxidization and reduction phenomena. Same material will give you different types of sensing phenomena. That is the interesting thing. So IEDs, the interdesiated electrodes, we purchase this kind of desiated electrodes where terminals will be there. We connect it directly in the circuit, and we, based on droplet phenomena, we coat on these materials, and then we study, we keep all this chamber, in the chamber, we keep this IED, and then we study the mechanism. Basically, I told you, like a response curve, we will be measuring response time, recovery time, and then how LPG concentration versus response is changing. And these curves are with respect to time versus resistivity. And you could see the selectivity. That means you use ethanol, acetone, NO2, LPG. You see the LPG, for LPG more selectivity is there. So from here, you can measure sensitivity, selectivity, response time, recovery time. Based on that, you can design different kind of things. This is one example I want to tell you. Similarly, RGO, this is also like X-ray diffraction, particle size, the same material with the different images, and then the same phenomena. This MgO2 also we did. Why I want to tell you here is we prepared hybrid nanostructures, means we also used here some of the bacterial proteins. We extracted bacterial protein, and this bacterial protein we added to these nanomaterials, and we could sense at room temperature. Temperature is decreased a lot due to this because it supports in oxidization phenomena or reduction phenomena, especially in case of sensing phenomena. This we recently patented also. Jaden, and we added bacillus powder to LPG sensing. There were increasing in interesting results actually. This is what about gas sensing. So let me repeat what all things we were discussing till now. The first point I was trying to tell you why nano, what nano, and then nature inspiration, and then coming to sensors, basic fundamental definitions of sensors, and then gas sensors, and then chemoresistor gas sensors, and then some case studies we did till now. And then coming to non-enzymatic glucose sensing. So don't worry about the words non-enzymatic glucose sensing and all these things. Basically, we want to measure glucose in the blood. So before you want to measure glucose in the blood, you need to understand what is the chemical formula of glucose, C6H12O6. The chemical electrochemistry of glucose need to be understood. So if you see glucose generally, you know very well, as on today, you know, diabetic, how much diabetic people are there. So, you know, glucose will be converted in the form of energy, and a liver will take, and there will be some phenomena will be there. I just don't want to go in detail. But however, there are possibilities of hypo and hyper. Increasing glucose levels or decreased glucose. These are the two possibilities are there where patients will suffer. So if you can monitor this level to uniformly, then problem is solved. Monitoring of glucose is one of the toughest area where people will be facing as on today. Like people want to monitor continuous monitoring of glucose sensing. That means generally we go once in a while to hospital, or once in a while we check our blood sugar levels. But if you have from saliva or from sweat, if you can measure continuously, you can monitor, then there will be, a patient could be treated very effectively. That is the one advantage of sensing. You know, there are a lot of side effects of glucose, like diabetes, like respiratory issues, high blood pressure, cardiovascular diseases. These are all some of the things where people are suffering. So, to solve this kind of things, first of all, we need to understand what is a biosensor. A biosensor is one where we will be using a biosample, a bioreceptor. A bioreceptor may be an antibody, maybe a bacteria, maybe a virus, or a tissue, or a blood, whatever it might be. There will be a transducer, and there will be a signal processing system. In this signal processing system, once again, you can measure current, you can measure voltage, you can measure resistance, you can measure impedance, because in a circuit, if you measure resistance, it will be an impedance. Simply, I can say the bioreceptors are like enzymes. Enzyme. It may be an enzyme. It may be an antibody, nucleic acid, bacteria, cell, tissue, or organelle. So these are all some of the things where people use as a bioreceptors, and from there you can measure. There are once again different phenomena like a pH value modification, heat, light, mass, even sound waves could be used in different kind of, like electrode, pH thermometer, photo detector kind of things people will use, and they'll use some amplifiers, and from there we will measure the signal. So this is what the concept of a biosensor is: a compact analytical device that uses specific biomedical reactions to detect and measure targeted compounds in the biological samples. A simple thing. The molecule recognition element includes receptors, enzymes, antibodies, nucleic acids, microorganisms, and kind of things will be possible. This is what a basic principle of a simple biosensor. Coming to a glucose sensor. There are different types of glucose sensors were there in the earlier. So if you consider, once again, electrochemistry of glucose, possibilities are oxidation and reduction. Once again, I tell you, if the fundamentals are same. In our intermediate level, whatever you study, glucose oxidation and glucose reduction, the same thing holds good here also. But you need to understand what are the different other factors are involving here and how to continue the research. So, there are different types of sensors, like first generation glucose sensor. What is the first generation glucose sensor? People used to measure H2O2, hydrogen peroxide levels. We used to measure in the beginning. There used to be a very big kind of mission where people try to understand the level of H2O2. Based on that, people used to measure glucose levels. After that, people started adding some enzymes there, gluconic acid and some materials like here, see, they will be kind of mediators. People started using mediators. They are the second level. And then coming to third, people also started some substrates like carbon-based substrates. People started using it, but they use enzymes here. When they use enzymes, as a simple example, let me tell you, some tablets will be good for some people and some tablets it will give side effects. Similarly, different depending on the type of the patient, if sometimes these enzymes will react with the concerned persons and show a wrong results of blood. So that is the reason people started non-enzymatic glucose sensing. So we work on non-enzymatic glucose sensing once again. So the drawbacks of enzymatic glucose sensors are like depending on the cofactors, turnover rate, selectivity of glucose. These are all some of the problems are there. As I told you, maybe amperometric, potentiometric, and resistive, chemoresistor kind of things are possibilities are there. So when you see the levels of the glucose sensors is increasing day by day, and people want to have a smart contact, and people want to work on smart contacts of sensors, like you have some smart contact from where you could see in a cell phone kind of things. These are the possibilities are there. And so here, I will present some of the interesting explanations like first generation, second generation, first generation, second, third, and 4th. These are all the, now we will be working in this. So here, especially we took core and shell nanoparticles. I just don't want to go too much into these. The basic point what I want to tell you here is, if you have a core and shell nanoparticles, sir, how much time I have? Like maybe another 20 minutes?
Sir, okay, sir, please proceed, sir.
No, you can tell me, no problem.
10 more minutes. If you
The
don't mind.
session is planned actually for 1 hour, sir. You can take another 5 or 10 minutes to complete, sir.
Sure. I will be doing that. Thank you very much.
Right, sir.
So, his core and shell nanoparticles will be there, where core and cell will oxidize slowly and reduce slowly in the comfort manner. So here, especially we prepared nanoparticles based on Osimum, Tulasi. Like Osimum is Tulasi, where we have a greenhouse where we develop different types of Osimums, like 4 or 5 types of, and then we prepared these nanoparticles. Then similarly, X-ray diffraction, particle size analyzer, UV, FTIR, scanning electron microscopy. Basically, what we do is we use this type of interdesiated electrodes, and this is the basic setup for electrochemical workstation, where we use reference electrode and one working electrode, which is our material. This is going to be here, and one normal electrode. So based on this, we will be studying different types of, we will be taking, we have a collaboration with some particular hospitals where we will take the blood samples, and from there we study this type of enzymatic, non-enzymatic glucose sensing, where we will be getting from cyclic voltammetry, we will get this type of curves. Based on these curves, potentiometric, how the potential difference is going to happen, and from there it is called potentiometric electrochemical gas and glucose, non-enzymatic glucose sensing setups, from where we can calculate all this type of, see, you could see here a core and a kind of shell particles. From there we can measure all these things. So this is what about the glucose sensing. Once again, a biosensor, and then coming to glucose sensor, basically non-enzymatic glucose sensing I was trying to do. So I work in Jawaharlal Nehru Technological University, and which is in Telangana state government. And then we have 10 districts and 8 constituent colleges. Under that 8 constituent colleges, there are one in Hyderabad, Karimnagar, Mantani, Sultanpur, and I work in Institute of Science and Technology, where ours is a unique institute. We run MTechs only. We don't run undergraduate level. We run MTechs and PhDs. So in this institute, we have 8 centers: Center for Biotechnology, Center for Chemical, Center for Nanotechnology. Ours is a DST Nanomission established center. And we run MTech in nanotechnology, PhD in nanotechnology, MS for international students. Our area of research in center are energy. We work on some of the energy materials. We also work on agriculture, seed germination, and pesticides, some of the pesticides. We also work on nanobio, like antibacterial, anti-cancer kind of things. Our main work is on sensors, once again, bio, gas, glucose, and humidity sensing, water pollution and absorption phenomena, and these are all some of the areas of our research. And coming to our kind of instruments, TGDTA, atomic force microscopy, X-ray, Raman is not working, ball milling, thin film, staplerosis, nanoparticle size analyzer, chemical vapor, cyclic voltammetry, solar simulator, hot air oven, and nanofluid, and contact angle instrument, FTIR. These are all some of our instruments. These are all some of the old students and present students who completed their PhD. And thank you very much for your interesting listening. Now I open for the session for the questions. If any questions are there, we will try to have a discussion.
Dear participants, you can ask any questions with Dr. Venkatesh Rao. Now open for questioning.
Sir, this is Murugeshan from SSN.
Yes,
yes sir, please. Sir, your talk is more informative, so we are getting a more point from your talk. So I have a small doubt. Sir, can we use the polymeric material for a substrate or a substrate? Shall we use it? What kind of polymer we can use it, sir?
Yes, you can use polymers. The problem is hydrophobic nature, kind of like water it will absorb humidity. That is a big problem actually. So you need to plan some way or other this kind of polymers. When you use polymers, humidity will attack that. So you need to have a separate humidity chamber, or you need to measure humidity also. That is one more important point. Yes, polymers can be used, could be used.
Okay, sir. Thank you. Thank you very much.
Thank you.
Sir, what is the impact of natural products in nano? For example, if you have a plant extract, how to get a nano material from that plant extract? Is there any ways to get it?
I exactly did not understand the question. Are you asking like physically? Are you asking a chemical kind of thing? I did not get.
Chemical compound based on natural products.
So natural products, basic point is here scales or scale matters. When you read, they are going to have different properties. When in coming to the normal things also, you need to understand what are the chemical compounds are there, and when you are reducing that, what exactly is happening based on that. We cannot generalize it, but depending on individual things, we can understand in a better way. Sir. That is that I can say here. Is it appropriate to your question, or I need to talk more?
Well, it's okay. It's okay. A little bit of thing is there. Okay, it's not.
Sir, how can we improve sensing properties of materials? One question from H.K. Sharma Garu. Sir, there are different. Once again, you need to go to fundamental way of understanding. How we can improve is like you can reduce the size, or you can morphology based, like depending on the type of the morphology, how you are working, and depending on the type of the kind of things, you can concentrate and work. Sir, actually, can we use the lab there? Yes, you can use, but you need Sheen Kumar N. You can use, but you need to have a prior information. What do you want to do? What exactly you want to do? Based on that, we can have a discussion, and from there you can start working, sir. Yes, from Tamil Nadu, lot of people will come and they started working. We have a common publications kind of things. I did not get mails, sir. Do you due to network issues? Please send feedback. Okay, this different thing. If any questions are there, even you can type it here in the chat box so that I can answer. What should be considered for importing self-cleaning and antimicrobial properties over biosurface? Yeah, you need to first of all understand contact angle information. You need to have a mission called contact angle mission. From there, you can go on adding different nanomaterials, and you can see the contact angle information. That is the first point you can say that we have. And other thing, like depending on your self-cleaning is once again a big area where you need to like once again like self-cleaning, like on the glass, on the cloth, on what kind of things you are working. The different physical phenomena are there. Like if you increase temperature, dust particle will move away. Are you using that phenomena? Otherwise, photo kind of chemical phenomena, like photochemical phenomena, where light falls on it, dust particle will be repelled by automatically. Kind of things you need to understand. Applicable water treatment. Yes, sir. Nanoparticles could be used in water treatment also. Like what is that once again you are doing? Like but due to absorption phenomena, some of the chemicals could be make as a precipitates by adding some of the nanomaterials. That kind of things are possible. But however, the fundamental things you need to have an understanding. Based on that, you can work, sir, actually.
Sir, I have one general question.
Please, sir.
Regarding the biosensors, how did the nanotechnology principle involve, for example, the predators catching its prey due to temperature sensors or color change in the predators? A bit biological side.
Sir, your question I could not listen because of some signal problem. But if you can repeat, it will be very good. But whatever, like I am understanding is, like you need to use different types of antigens in the body.
Yeah.
And then you need to use different types of basic fundamentals only. But the beauty here is as the size surface morphology is changing and surface energy is increasing, due to that, the properties enhances that you can use, sir, actually. What are the properties? Let us take gold nanoparticles. I was trying to tell you. So I was doing in my postdoctoral research in Johns Hopkins, imaging of cancer cells, especially CXCR4 protein. We were working on surface enhanced Raman spectroscopy, where we will be using nanoparticles somewhere so that the surface enhancement will be happening. Due to that, Raman peaks will be more predominant. That is what. So somewhere or other, whatever the science you know, whatever the technology we know, we want to incorporate some of these ideas such that you will be getting a more predominant values. That is what the concept actually.
Sure, sir. Sure. Now it's over to Dr. Stanley. If there is no further questions
from the YouTube side, from the YouTube side, there is one question, sir. What is the advantage of metal oxide nanoparticles for sensor application?
Yeah.
What is the advantage of metal oxide nanoparticles for sensor application?
Thank you. Metal oxides are generally P-type or N-type materials. So P-type or N-type material, whatever the concept I was trying to tell you, oxidization phenomena and reduction phenomena will be very interesting, and that could be explained in a very effective manner. And then sir, can you explain how testing kit works for corona? I actually don't know much about that corona testings, actually, frankly speaking. But basically, they use some antigens, and from there, they have some strains, actually. They took some strains, and that strains, they are comparing it, actually. Without contact, the physical contact. Thermal scanning sensor. Thermal scanning sensor is basically a temperature measurement. It won't do corona kind of things, because if your temperature is high, people will one of the corona positive thing is like people will have more temperatures. They will get fever. So that is the reason people were using it, actually, frankly speaking. That is what I could understand.
Right, sir. Thank you, sir.
Sir, one basic question from my side.
Please, sir.
Hello.
Please,
sir. Basically, I'm an organic chemist. I want to work in a nano in which I synthesize more than 180, 170 compounds when you are having a medicinal property on the side. How to convert that compound into nano level to test with some other aspects of
my advice is rather than converting them, dendrimers will be there, like a dendrimer kind of structures. Somewhere you can add some nanoparticles for some type of applications, basically.
Okay. Because I'm working in a carbazole related things, I want to explore that carbazole related thing nano. Because when organic electronics comes under this one, because it is the application side in a college like engineering college, it's very difficult to work in a wet lab. So I want to just shift over. That's the reason I asked.
So you add somewhere nanomaterials in dendrimer structures or somewhere if you can incorporate, and based on that you can prove by mass spectroscopy or something, and from there you can do one application. If the application is giving good results, then you can explain more science kind of things. That is what I can address.
I'll text you in the mail, sir, if it is possible.
Thank you.
Sir, I have a question. I have one question, sir.
Better if it is combining all the people talk together. If you type in the chat box, maybe best.
I have typed. I just want to know, I'm just a beginner for nanotechnology. I just want to know, how do you find out that the nanoparticle so synthesized is of the diameter of your choice?
Yeah. You need to go for transmission basically, you can do X-ray diffraction. From there, you can get crystallite size.
Okay, sir.
And then you can go for scanning electron microscopy. You can see the almost all near to micrometers range. If you go to transmission electron microscopy, you could see very clearly. But however, you need to understand the chemistry of the reaction. What is happening, how pH modification, temperature modification, pressure modification, time, chemicals, what you are using, reactants, all these things are matters actually. So template assisted methods, there are n number of methods are there on synthesis phenomena actually. So basic chemistry you need to understand, you need to expect something based on your chemistry, and you need to check with the characterization techniques.
Okay, sir. Thank you, sir.
Sir, I have a question, sir. There are many methods like chemical, physical, and biological methods for synthesizing nanoparticles.
Exactly.
So, can you explain something about biological method, like using plant extract, animal, bacteria, fungi, algae, and kind of, because they are more non-toxic, and they are also the nanoparticles prepared using biological methods. I read in literature it's very stable. They don't agglomerate. Also,
so
biological products. So,
mainly biological synthesis, let us say green synthesis. If I say green synthesis, use some leaves and things, the reproductibility is a big problem actually in case of that. But however, the basic thing is they will be using as oxidizing or reducing agents to prepare final compound actually. So that is the green synthesis. Coming to the bacterial protein and other kind of things, yes, depending on your application, you need to select this type of materials. Once again, this is all synthesizing itself is like chemistry. Big molecules they synthesize and use for some application. In our case here, nanomaterials generally based on the application requirement, we go in reverse manner. Like we will be selecting different types of material. Physical methods are you can do physically, like see, let us say graphene is there. You can prepare physically, you can prepare chemically. If you prepare physically, exactly you can prepare. Why? Because we'll be using different types of big instruments where you will be giving some equal current, equal resistance, voltages like that. Whereas in chemical point, you need to be precisely do chemistry actually. You need to understand the basic reaction and then you need to work on it actually.
In case of biological preparation, we don't need such expensive instruments, right, sir?
Yes, but however, we need to be very careful when we are working biological synthesis.
I don't see much work going on in the field of...
Exactly. So self-biological synthesis materials are also coming up. Let us say, I will tell you civil engineering applications. Like if you grow some bacteria in between the cracks will be closed automatically. Kind of bacteria are available as like people are trying to work naturally, it will happen actually.
Okay.
So these are all some of the things, interesting phenomena people are working actually. So you can just Google it and you can work it out. Actually.
Thank you, sir. Thank you very much.
Thank you very much.
Sir, there is no further questions, sir. So I want to thank you for a wonderful and a fabulous presentation. All our participants are very much benefited by your lecture, and it is reflected in the feedback. We are able to see wonderful feedback from the chat box as well as from the YouTube chat box. So really, we are very thankful for the wonderful session you conducted for our participants, sir. And we are very privileged and we are very much honored to have you among our midst. Now, I want to say something about the feedback. Some participants, they repeatedly say that they are not able to give the feedback. The feedback link is working properly, and if you are not logged into your account, it may not work for you. So if you try to log into your account properly, and when you try to do the attempt that feedback, definitely you will get it. So we will be waiting for another 30 to 40 minutes or even 1 hour to close the feedback. So kindly make use of the time, and if you have any problems in giving the feedback, please mail me. I have given my mail ID stanley@svce.ac.in. So that is the mail ID you can make use of. And we cannot share this feedback in the WhatsApp group, because sometimes it is being misused by the people. That is why we are not encouraging to give the feedback in the WhatsApp group. So if you have some problem, just mail us and we will resolve all your problem. Thanks for your time and thanks for your cooperation. And in the afternoon, we have Dr. M. Venkateswara Rao.
Sir, one more request. Sir, may I request Dr. Venkateswara Rao to suggest a few concluding remarks or suggestions? The speaker.
Let me finish and he will continue, sir, because there are so many queries are coming in the chat box. So afternoon session, we have Dr. M. Venkateswara Rao AGM R&D lithium ion battery, and the session will start by 4 o'clock, and I asked the participants to be there at 3:45 p.m. in order to avoid any connectivity issue. And his topic is perspectives on energy storage technologies. Many people are asking about the topic, so it is given in the FDP brochure as well as in the program list. So kindly check that for all the informations. Right now, may I request Dr. Venkateswara Rao to give the concluding note.
I conclude that thank you very much for the opportunity, and thank you very much, participants. You have asked an interesting questions, and I wish you all the best. Thank you very much once again.
Thank you, sir.
Thank you, sir. Thank you so much, sir.
Thank you once again, sir. Thank you.
Hello.
Participants, if you have given the feedback, you may leave the meeting if you have some work. And if anybody is having some problem in the feedback, kindly stay and we will resolve all your problems.
Hello, sir. Is it possible to share the PPT of this webinar, sir? Hello. My name is Sandhya.
We will discuss and we will let you know once if the resource person has given all the materials to us, we will send it, right?
Fine.
And you can watch all the recorded programs in the YouTube channel, right? So absolutely no problem. Everything is being recorded and it will be there forever in the YouTube channel. You can make use of that as a resource material for your future reference.
Sure. Okay, sir. Thank you.
Sir, I'm leaving now, sir. I'll join.
Yes, madam. Yeah, you can go.
Thank you, sir. Bye, sir.
Right, madam.
Sammy, everything gone well?
Yes, sir. Wonderfully. இன்னைக்கு ஒரு technical problem கிடையாது. A very excellent session. We had a wonderful time with the thing. And நேத்திக்கு தான் because of connectivity issue we struggled a lot. So by God's grace, everything went on fine. And Dr. Anand Babu has chosen a very right person. Excellent presentation. Very informative and very interesting.
அதாவது அவரு அந்த டிஸ்கஷன் எடுத்ததுக்கு முன்னாடி எத்தனை ஸ்லைட்ஸ் அந்த கண்டென்ட் ஒரு இதுவும் ஷேர் பண்றாரு பாருங்க.
ஆமா, அவர் கேட்டாரு கரெக்ட்டா நான் டைம் ஏனோ 20 நிமிஷம் எடுத்துக்கலாமான்னு கரெக்ட்டா அவர் முடிக்கிற ஸ்டேஜ்ல தான் கேட்டாரு. கரெக்ட்டா நான் சொன்ன பிறகு ரெண்டாவது ஸ்லைட்லயே அவர் கன்க்ளூடிங் செஷன் கரெக்ட்டா அமைஞ்சிருந்துச்சு அந்த மாதிரி.
சூப்பர், குட், வெரி குட், வெரி குட்.
Sir, anybody facing feedback, you please let us know. Don't carry till late night. Because till 10 o'clock, 11 o'clock, people, they keep on asking. So please, if you have any problem, because we have another one session in the afternoon. So we have to close this feedback session at the earliest. Sir, நான் லைவ் க்ளோஸ் பண்ணிடுறேன் சார்.
எஸ் சார், இந்த ரெக்கார்டிங் இந்த கூகுள் மீட் க்ளோஸ் பண்ணிடலாம்.
ஆமா, அதையும் க்ளோஸ் பண்ணிடலாம். இனி நம்ம பர்சனல் chat தான். You can close the Google Meet recording as well as I will end the live session.
Okay, fine.